So welcome back. Another quick review or tutorial, this time on the main points of Chapter 8, confidence intervals. So the main objective of Chapter 8 is to calculate an interval around what is called a point estimate. Now, a point estimate is a single statistic. It's one statistic that you calculate from your sample. In this chapter, or in Com 215, that single statistic is going to be the average, the mean. And so why do we calculate this average? Because, as we've discussed before, we usually cannot observe the population, and therefore we cannot calculate the true population parameter for that average. And so the next best thing is to take a sample. So once we take the sample and we calculate its average, what do we do with that average? So what we can do is we can create an interval around that estimate. We essentially create an upper limit and a lower limit. And those limits are supposed to, in theory, contain the real population average with some degree of confidence. So we don't know where mu is, we never do, but if we take a point estimate and create a confidence interval around it, that interval should contain the real average to some degree. Okay? So the probability that the confidence interval will contain the population mean is actually called, or is actually denoted by 1 minus alpha. I know we've talked about alpha before. Essentially, it's a level of error that you're okay living with. There's always going to be a little bit of mistake that you're accepting, or you accept. And so 1 minus alpha is called the confidence coefficient, whereas 1 minus alpha in percentage term is called the confidence level. They are interchangeable, but please don't confuse the two. So in general, the probability is 1 minus alpha that the population mean is contained within that interval. And how do you calculate the interval? It simply starts off again with the point estimate. We'll call it that PE. And then we're going to add or subtract a normal number. And I've talked about this before. I usually give it the analogy of being the number of steps taken away from the point estimate, whereas the standard error here, I called it the size of each step. Okay, so this should take you to the right and to the left some value, and again within those two values the real population average should be, or in theory should be. Pretty straightforward idea. The only complication that arises is what happens when your sigma is unknown. So when you do not know sigma, your calculations cannot be as exact, and so you have to use some sort of estimate. So let's assume that you know that the population is somewhat normal looking, but you don't know the real sigma. So what you end up using, or what you end up needing to use, is what is called a T-distribution, which is very similar to the normal distribution, except it's a little bit more of a warped or variation on the normal distribution. And you can see here, in this particular case, it's wider. It's still symmetrical in bell shape, much like this normal distribution, except it's wider. So it's spread. And that spread is given by what is called the degrees of freedom. And so this is one of the determinants of the curve. So you have an infinite number of these curves, and each curve is identified or determined by its degrees of freedom. And this degree of freedom is equal to 1 minus n. And so if you have a sample size of 21, then degrees of freedom are equal to 21 minus 1, which is 20. And so when you're looking up the values in a T-distribution, you have to know what is the degrees of freedom. A couple other points here. As the sample size increases, the degrees of freedom also increases. That makes complete sense. As the degrees of freedom increase, the spread of the T-curve actually decreases. What that means is that as the degrees of freedom increases indefinitely, so the larger and larger the sample size is, the T-curve approaches the T-standard normal curve. So essentially, it converges onto the Z distribution. It becomes the Z distribution. And we can really see that starting to happen as soon as your n is large, meaning greater than or equal to 30. A pleasant consequence of actually knowing sigma is being able to calculate the sample size n that is needed so that your confidence interval is within some value of E, the margin of error. So let's say you have a sample, and that sample, let's say, is 5 kilograms, and you would like to estimate the interval to within 2 kilograms. So basically 5 plus or minus 2 kg. You can do that, but you can find the sample needed to be that precise, especially when you know the standard deviation sigma. And so all you need to do is plug into these values here, here, and here. We'll do an example, and you're able to calculate the sample size. One point I'd like to make, and this is a very important point, let's do a quick example. Let's say you have a sample, again, 5 kg, you have 5 kilograms, and it says your standard deviation is 1 kilogram, and your sample size is 16, and so therefore your degrees of freedom are equal to 15, and somebody asks you to find the sample size needed in order to estimate the confidence interval to within 2 kilograms, right? So let's make it even more difficult. Let's half a kilogram. And so naively, a lot of people, what they would do, and they'll just replace the Z with a T and the S here, and here's the E, and square them. Now this is completely wrong. The reason being is that you'll get stuck on this portion right here because you need N in order to find T, and you're trying to find N, so it's very recursive, you see? So please don't do that. It is not going to end well in terms of finding a solution, right? So this and this are needed within each other, and so it's just going to become very recursive. So if this is ever asked on an exam or in general, what you do is you just make a simplifying assumption, and that simplifying assumption is you say, okay, well, you know what? Let me think, or let me assume that the standard deviation of the sample, instead of calling it S, let me call it sigma. Let me assume that it's the population standard deviation. And when you do that, it's a simplifying assumption, but at the end of the day, it helps you solve the problem because a lot of times your N is going to be large enough that you're going to be using Z anyways. And so the answer is going to be large enough that it becomes large enough to use the Z. So we're going to look at that, I think, in some of these problems, but something to watch out for all the time. One final point in chapter 8 to be aware of, and it's no big surprise, we've seen this before, you can actually calculate confidence intervals for population proportions. Just like in chapter 7, where we dealt with finding probabilities after a certain value, but then now we can do them for proportions as well, and this is the same exact idea. So if N is large, again, just a small reminder, N is large when N times P is greater than or equal to 5, and N times 1 minus P is greater than or equal to 5. Both of them have to be valid and true. And so when N is large, you use this formula in order to calculate your confidence interval. Okay, so exactly the same thing. This is your sample average. This is your point estimate. And then here you have your standard normal value. This is the number of steps. And of course, you can't forget that this expression here is simply your standard error that we've seen in chapter 7. And so pretty straightforward, and it also applies to calculating the sample size. So when you calculate the sample size, again, we're solving for N. It's the same concept, except the formula just changes a little bit. And so you have a variation on the one we saw above right there. And that was a really quick summary of the main points of chapter 8.